Good evening, everyone, and thank you for joining us for this live stream presentation, The Galaxy Menagerie, with Dan Reisenfeld. I'm Siobhan Nicholson with Pajarito Environmental Education Center, PEEC, located in Los Alamos, New Mexico, and I'll be tonight's moderator. Tonight's talk is being recorded. We're able to offer programming at this time because of our wonderful members and donors, so I'd like to thank you again for your support. We couldn't do it without you. Okay, and with that, I'm going to introduce Dan. So Dan first came to Los Alamos.
We'll find out.
We'll find out. He first came to Los Alamos in 1998 to design space instrumentation for various NASA missions after getting his PhD in astronomy from Harvard. After 6 years at the lab, he spent the next 14 years teaching physics and astronomy and continuing space research at the University of Montana. But he missed the land of enchantment, so he returned to Los Alamos in 2018, and now he's building instrumentation for the NASA IMAP mission to explore the interstellar boundary where the solar system ends and the rest of the galaxy begins. And I guess that will take us right into our talk about the galaxies that are out there. Take it away, Dan.
All right. Yes, well, thanks again, everyone, for coming. And please do, if you have questions as they come up. We will take questions at the end, but also feel free to type in your questions as we go along. This is an unusual format for me. I'm much more used to an interactive kind of engagement. So we'll try to make it as interactive as possible, but that's kind of up to you too. All right, let's see. Let's move along here. So to begin, we're going to be talking about galaxies outside of our own galaxy, but I wanted to spend some time talking about the story behind how we even knew that there were other galaxies. So you see here an image of the night sky, and you can see arcing across this image from Monument Valley. You can see the Milky Way. And I wanted to point out something about the Milky Way. You'll learn more about what exactly it is as we talk here, but basically what you're looking at is a band of dense stars, and you can also see in this picture lots of dark regions. And those dark regions we understand now are actual clouds, interstellar clouds, molecular clouds. A lot of these regions are actually star formation regions, but it wasn't always understood that that's what they were. But nevertheless, we did understand that we somehow were associated with this band in the sky, that we were part of this lane of stars and light. But we did not appreciate the sense of scale of the universe until pretty recently, really until the last century. I would say this century is because I'm an old fogey, I guess now, but until the 20th century, we didn't appreciate it. So I'm going to take you back in time a little bit to the first astronomer who actively tried to understand the scale of the universe. This was William Herschel. He was a astronomer in the 1700s and 1800s. He was a classic gentleman astronomer. He was, kind of, he didn't have to do anything else except do astronomy, so he had lots of time on his hands. And he's renowned in history now as being the person who discovered the planet Uranus, which was the first planet discovered since antiquity. And so that was a really big deal. And when he discovered Uranus, it became an international star. He also was really good at making telescopes, and he even is known for discovering infrared light. He also built the largest telescope of his time, which you can see here, which was about 40 feet long, this tube here, and it had something like a 20-inch or so mirror at the back of it. It was a reflecting telescope, so you actually had to stand up here in this little cage and peer down into the tube to see the reflection of the focused light that was coming in here. So it was very awkward to use at the time. Nevertheless, he was responsible for identifying lots of things in the sky, not just stars, but what we now call nebula. And but he also tried to map out the distribution of stars in the sky, and he proposed a model for the Milky Way, which looks like this. And so this is known as Herschel's Milky Way from 1785. And he got a few things right. He recognized that it was kind of flat and pancake shaped, that it was the extent, what I'll call north-south here, although those aren't really real meaningful directions, but up and down, that the galaxy was thinner than it was east-west. You notice also that there are these regions that seems like the galaxy doesn't go in as far, or that there's these fingers here, and that is because of the dust lanes that obscured stars, and he either didn't appreciate or just couldn't see any stars off in the direction, so he just assumed that there weren't any stars there. He also assumed that the sun was at the center, because he saw just about as many stars off in this direction as he did off in the other direction. So we must be at the center, which of course made everybody happy. But in fact, he was not quite right in that regard, because actually in the region where all those dust lanes were, that was in the direction towards the center of the galaxy. But we didn't know that yet. A little bit later on, another astronomer, Jacobus Kapteyn, a Dutch astronomer, also mapped out the distribution of stars in the skies, and he was the first person to put a scale to the size of the Milky Way, to actually place distances associated with actual distances. He did this by assuming we knew by this time the distance to some of the nearest stars, and by scaling the way in which the intensity of starlight dropped off with distance, he was able to kind of figure out how far away the fainter stars were. And so in his universe, the sun is not at the center. It's over here, whereas the center is over here. And that's a little more accurate. And the scale for his universe was about 50,000 light years from one end to the other. Now, this is measured in a unit called the parsec, and there's roughly 3 light years to the parsec. So 8,000 parsecs, which is the distance from the center out to the edge here, is about 25,000 light years. All right, now I'm going to be throwing these terms like light years out a lot, so I just want to make sure we all understand what a light year is. So here you have a little definition. A light year is the distance light travels in a year. So it is not a time, just to be clear, it is a distance. So it's in fact 1 light year, it's abbreviated as LY, is about 6 trillion miles. Okay, that's a fairly meaningless length to us. It's hard to imagine 6 trillion miles. So to put it into some perspective, the distance to Neptune is 0.0005 light years. Neptune I'm choosing because it's the furthest planet from the sun. At the moment, actually. It and Pluto are about the same distance away right now. That distance of 0.0005 light years is actually a distance of 4 light hours. That is to say, the distance light travels in 4 hours. Another way to put the light year into perspective is that the nearest star to us, Proxima Centauri, is 4.2 light years away. So the light we see from the star Proxima Centauri left that star 4.2 years ago, because light travels at a finite speed, and it took that amount of time to get to us. So now, going back to our universe here, Kapteyn figured out that our universe was about 50,000 light years across. Okay, well, was he right? Well, he was pretty close, but we'll get on to that. Now, here is the modern view of the Milky Way. This is an illustration. You cannot see the Milky Way. We have not flown anything far enough from Earth to actually get a view of the Milky Way from the outside. We'll have to wait until we have a warp drive, I think, for that. Anyway, but this is our best compilation of data to create a map of the Milky Way. And so here we are, the sun in this coordinate system is a sun-centric coordinate system. The sun's down here, but the center of the Milky Way is up here in the middle of the image. And that distance there is, in fact, about 25,000 light years from the sun to the center of the galaxy. In fact, the whole diameter of the galaxy from side to side is about 100,000 light years. So we are not at the center. We're not way out of the edge either, but we're, you know, kind of in the suburbs, so to speak. Okay. All right, now, to continue on, that describes our galaxy. And for a long time, until the beginning of the 20th century, that's pretty much what people thought the entire universe was. Except there were things in the sky that didn't quite make a lot of sense to some astronomers. They didn't really know what they were, and there was a lot of debate about what their composition was, what they actually were. An example I will show you here is in the constellation Andromeda. So you're actually looking at a fairly big chunk of the sky. I've traced out the lines for part of the constellation Andromeda here. You might notice also the constellation Cassiopeia, which is a W here. So this is, which is a pretty big constellation as well. But I wanted to point out this fuzzy little thing right here. What is that? An astronomer may ask, and of course, astronomers, zoomed in with their telescopes. And because it was in the constellation Andromeda, they call it the Andromeda something. So here's a zoomed in picture of it. For the longest time, this was called the Andromeda Nebula. It was thought to be just basically a gas cloud. There are lots of real gas clouds that glow in the galaxy, and this was just kind of considered to be one of those. But we may have another name for it, the galaxy. The problem is, how far away is this thing? It could be something relatively star-sized within our galaxy, or it could be something really big but far away. And it wasn't obvious what the right answer was. So in around 1920, in astronomy, we had what the equivalent was of a prize-fighting match between two giants of the day, Harlow Shapley and Heber Curtis. And they carried out a debate at the Smithsonian Museum of Natural History in Washington on the 26th of April, 1920. And every student of astronomy has heard of this at this point in time. It's known as the Great Debate, and it was entitled The Scale of the Universe. So in this corner, we had Harlow Shapley, the director of the Harvard College Observatory. And he was of the opinion that the Milky Way was the entirety of the universe. There was nothing beyond the Milky Way. And he had some arguments for it. And basically, the issue really came down to Andromeda. He claimed that spiral nebulae are gas clouds inside the Milky Way. There was a nova seen in Andromeda, which briefly outshone the entire Andromeda Nebula. And at that time, in our galaxy, novas were seen fairly often. Now, this is not a supernova, to be clear. Supernovas were not discovered, or none happened in our galaxy in modern times until hadn't quite happened yet. But nova happened fairly often. A nova is basically something we understand today when you have, say, two stars in orbit around each other, and one of those stars is what we call a white dwarf, and some material from the other star falls into the white dwarf, and when it hits the surface of the white dwarf, it ignites into a brief fusion reaction, which causes the thing to glow very brightly for a few days or weeks, and that's a nova. And so the fact that a nova was seen in Andromeda and it was as bright, it became as bright as the entire nebula, he argued, well, if it was something happening in a distant galaxy, that would be impossible because nothing could outshine the entire Milky Way, which would be the equivalent of a nova going off in Andromeda. So he argued that Andromeda must be close such that nova were not ridiculously bright. There was also another astronomer named von Manen who had measured a change in the rotation of one of these other nebula called the Pinwheel Nebula, and I'll have a picture of it later on. Basically, he looked at it and then came back to it a few years later, and to him, he thought he could see that it had rotated a little bit. Well, if it was truly something outside of the Milky Way, if it had rotated enough in the time span of a couple of years to be detectable, it must have been rotating at faster than the speed of light. So therefore, since that was impossible, he concluded that the Pinwheel Nebula was inside the Milky Way and much closer in order for that rotation to be possible. And finally, Shapley had an estimate for the Milky Way to be much larger than the 100,000 light years. He thought it was about 300,000 light years in diameter. And he couldn't conceive of something being outside of that. And that was just, for lack of a better explanation, just a failure of imagination on his part. Okay, now in the other corner, we have Heber Curtis, who was the director of the observatory at the University of Michigan. Now, he was of the opinion that spiral nebulae were what were known as island universes at the time. The term galaxy had not quite caught on yet. So the Milky Way was an island universe, and these other nebulae were other island universes with vast spaces of emptiness in between them. This was a pretty radical concept. He wasn't the first person to come up with it, but he was the first person to have empirical evidence to support it. So he argued that Andromeda is the same size as the Milky Way, which means it's very far away. He also pointed out that there are more novae seen in Andromeda than in the Milky Way itself. So in other words, you saw the picture of the of Andromeda. Every so often, a nova would be observed in it, maybe not as bright as the one that Shapley argued was too bright to be reasonable for something far away. But nevertheless, many nova were seen in Andromeda, more nova than were seen in the Milky Way. And so he argued, what's so special about this little piece of sky that there would be so many nebula in it, or sorry, so many nova in it? And he argued that it must be an entity of its own with many, many stars within it that occasionally would go nova. He also noted that galaxies, or these nebula, often had dark lanes in them, similar to the dust clouds seen in the Milky Way. So by analogy, he argued that these must be like the Milky Way. He also claimed that this Pinwheel Nebula motion observation was an error. He just nope, they were wrong. And also, he argued that the Milky Way is smaller than what Shapley thought. He put the Andromeda only needed to be 2 to 3 million light years away, which was a somewhat more conceivable distance to at least some astronomers. Well, history has proven that there was a winner to this debate, although it wasn't resolved on the 26th of April yet, and that was Curtis. He was right. The pinwheel motion observation by von Manen was an error. It did not move. So that shot down Shapley's argument on that. And in fact, Curtis said during the debate, if it turns out that the pinwheel rotation was truly a reproducible observation, he would concede to Shapley. But it turned out to not be true. Okay, so how is it that we figured out then that Andromeda was outside? Because this is all circumstantial evidence. Nobody's proven anything here yet. These are just arguments on both sides. It only took 3 years for the evidence to come in. But before I can explain that evidence, I have to go back a little bit to another astronomer, Henrietta Leavitt, also of the Harvard College Observatory, but she was working there before Shapley, and she's now gotten a quite bit of renown, but at the time, few people had heard of her because, of course, female astronomers were not to be taken seriously. At the time, I'm pointing this out to you. Certainly now we take them very seriously. Anyway, she came up with a curious relationship between certain variable stars and how bright they were. These stars are called Cepheid variables. It's a certain class of variable star. Now, a variable star is a kind of star that pulsates on time scales of weeks to months to years even. They change in brightness. They get brighter and then dimmer and then brighter and then dimmer. And you can go back, you know, in reasonable amounts of times and track their changes in brightness. So Henrietta Leavitt, who was an excellent observational astronomer, noted that there was a relationship between the period of the pulsation and the brightness, and that if you took the logarithm of the period and the logarithm of the brightness, which was a unit called a magnitude, it fell on a straight line here, and it was given by this formula down here. Don't worry about the formula. The point is that there was this very curious relationship between period and brightness. This was discovered by Henrietta Leavitt in 1908. And as I said, it links the intrinsic luminosity of a star to its pulsation period. Now, that's curious, and certainly we would like to know why that was true, but she realized that it could actually be used as a means of measuring distances. Because if you compare the intrinsic luminosity of a star to its apparent brightness, you can figure out the distance to that star. So let me explain what that means. So intrinsic luminosity is the equivalent to, like, if I have a 100-watt light bulb, its intrinsic luminosity is 100 watts. No matter how far away that 100-watt light bulb is from you, it's still giving off 100 watts. But it'll appear dimmer the further and further away it is, or the further and further you get away from it. So one could wonder, suppose I also had a 50-watt light bulb, and I moved that far away from me as well. Which one is closer to you? Suppose you didn't know one was 100 watts and one was 50 watts. Suppose they appeared to be the same brightness because one was, the 100-watt light bulb was further away than the 50-watt light bulb. Unless you knew their distances, because you could walk and measure the distances, you wouldn't know which was the 100-watt bulb and which was the 50-watt bulb. Well, what if I told you that the 100-watt bulb blinked once a second, and the 50-watt bulb blinked once every 2 seconds? So now you have this thing blinking away at once a second, another thing blinking away at twice a second. And so all you need to know now is the thing that's blinking once a second is the 100-watt bulb, and the thing that's blinking twice a second is the 50-watt bulb. And now you know by measuring their apparent brightness, which one is further away than the other. And so this is effectively what this period luminosity relationship tells us. By looking at how quickly the stars are blinking, basically, we can figure out their intrinsic luminosity, and then by measuring how bright they appear to be in the sky, we can use that difference to figure out how far away that object is. Okay, now one of the nice things about these Cepheid variables are the really intrinsically bright stars that, in fact, they're so bright that you can see individual Cepheids in distant galaxies. And so that means if you see a Cepheid in a distant galaxy and you can measure its pulsation period, and you measure its apparent brightness and compare that to the period luminosity relationships, intrinsic brightness, you can figure out how far away that Cepheid is. And that is what Edwin Hubble did. He determined the distance to the Andromeda Galaxy using the Cepheid variable relationship determined by Henrietta Leavitt. He discovered a Cepheid in Andromeda. And using the period luminosity relationship, he put the distance to the Andromeda Galaxy, or that Cepheid in Andromeda, at 1 million light years away. And that was even beyond the edge of Harlow Shapley's Milky Way. So we've had proof, and I didn't put the date here, but this was in 1923. We now had evidence that Andromeda was outside of the Milky Way by quite a lot. And thus, extragalactic astronomy was born. All right, well, I would ask if you had any questions at this point. In fact, I'm going to take a drink here, so I'll pause for a moment before we go on to the next chapter.
And just as a reminder, this is Siobhan. If you do have questions, feel free to put them in the chat, and Dan would be happy to answer them as they come in.
Yes. So, okay, I think I'm ready to continue. Oh, modern distance. Oh, so by the way, the modern distance to Andromeda is 2.5 million light years. So the calibration of the Cepheid relationship hadn't been completely formally worked out yet, but it still gave the right answer to within about a factor of 2. All right, now, this is what we call the local group of galaxies. There's a distance scale here of 1 million light years. Here's the Milky Way in the center. Andromeda is over here, 2.5 million light years away. And then there's all these little guys here, which are what we call dwarf galaxies, which are all part of what we call the local group. Actually, deep in here, they're not called out, but there's a couple of things here that aren't labeled, and those are the large and small Magellanic clouds, which are also part of the local group of galaxies. So thanks to the Cepheid relationship, we were able to start to map out not only the arrangement of galaxies in the sky, but also how far away they were from us, and we were developing a 3-dimensional picture of the universe. Well, that whole thing is another story, mapping out the structure of the universe. And I'm not really going to be talking about that today. The next part here is just to kind of talk about just the different kinds of galaxies there are. What do they look like? How do we organize them? And what we can learn about the evolution of galaxies by their structure. So galaxies fall into 2 basic types. There are the spiral galaxies. And here's a beautiful example of a spiral galaxy, NGC 1566. By the way, NGC, you'll see that number a lot, means New General Catalog. And it was a catalog made in the 1800s, so it's not new anymore, but we still call it NGC. It was a catalog of nebulae. Many of them were galaxies, some of them were other things like planetary nebula and clusters and things like that. It's sort of similar to the Messier collection of objects. Anyway, but NGC designations are still used today for things. Anyway, spiral galaxies like this one have about 1 billion to 1 trillion stars in them. The Milky Way, for example, has 100 billion stars in it, so it's a rather large spiral galaxy. The other class of galaxies are what we call elliptical galaxies. And this is an elliptical galaxy. It's Messier 87 or NGC 4486. For astronomers, this is actually a very important galaxy, and I'll get to that in a little bit. In general, though, elliptical galaxies are ball-shaped or ellipsoidal shaped, and they have 1 billion to something like 100 trillion stars. So, in fact, M87 is an example of one of these supergiant elliptical galaxies. And think of that, 100 trillion stars, that's 1,000 times more stars than the Milky Way galaxy. So elliptical galaxies can become enormous. And they are nevertheless not all that interesting to look at. I mean, spiral galaxies, that's where all the photographers run. That's where the beauty is. Elliptical galaxies are rather uninteresting. I mean, the most interesting things in this picture are the other things in it. Like there's 2 spiral galaxies that you can't quite make out down here. That's a star up there. Anyway, but nevertheless, about a third of the galaxies in the sky are elliptical galaxies of some kind. 2/3 are spiral galaxies. So those are the basic 2 types. But we didn't rest at that. In fact, Edwin Hubble, again, was responsible for establishing a classification scheme to make sense of all the different shapes and sizes of galaxies. And here is a page from the Hubble Atlas of Galaxies. It's named in honor of Hubble. It actually was written by Alan Sandage. It's actually it's an atlas with lots of beautiful photographic plates in it of different galaxies. And this is just a list of the galaxies in it. And I wanted to point out to you, you can see the NGC numbers on the left-hand column, and then there's copies over here. There's another set of galaxies and their NGC numbers here. But over here we have type. And if some of you may have actually looked at a Galaxy Atlas or seen these numbers before and wondered, or numbers and letters, what these actually mean. So you see like SO, SB, SC, E1, E3, and then there's some like SBA, and then in parentheses, little s, and then next to that, PEC, that, or actually it looks like that says PEE, but it should be PEC. Anyway, and then there's all these different designations. Those designations were a set of designations that Hubble made to classify different types of galaxies. And this is his classification scheme. Its nickname is the Hubble tuning fork. And so what he did was he has on the left side of the scheme, he has all the elliptical galaxies. And they're labeled by E for elliptical, and then a number. And the number is the degree of eccentricity to the ellipse. So something that's perfectly round is an E0, and something that's very sort of oblong has a higher number. So this is like an E7. And then there was a class of galaxies called S0 galaxies, which are, they're kind of like elliptical galaxies, and they're kind of like what's over here, which are spiral galaxies. And then there were 2 branches of the spiral galaxies. There are the S, A, B, and C galaxies, and then there are the SB, A, B, and C galaxies. And the difference here is the B stands for bar. So you can see in these galaxies here, there's a spiral arm, but then there's this bar across the middle, and then the spiral continues on the other side. Again, there's a bar in the middle, and then the spiral arms kind of extend off of that. And here's even one where the bar is, you can see the bar, but it's the spiral arms are not quite as clearly defined. And in fact, that's what the A, B, and C correspond to up here, and up here as well, is the A, B, and C correspond to the tightness of winding. The pictures aren't as good as showing it as the illustration. So an SA has loosely wound, or tightly wound spiral arms. The SBs, the winding's a little looser, and SCs, the winding's even looser. And I'm going to show you now a bunch of examples of different ones of these, and we can try to guess how Hubble would have classified them. So, okay. So now we're going to, first I need to give you a more detailed list of the classification scheme here. So as I said, there are the E galaxies, which are elliptical galaxies. They're labeled E0 through E9, where 0 is circular, 9 is highly elliptical. Don't worry, there will not be a test at the end. This is just for your amusement. Then there's the S0 type galaxies, which are the ones at the base of the fork. And those are called lenticular galaxies, and they're described by diffuse halos, significant dust lanes, and no spiral arms. Then there are the spiral galaxies, SA, SB, SC, even SD, where A is a tight winding and D is a loose winding. And there's also middling classes like SAB, which is between an SA and an SB, SBCs, and so on. And then there are the barred versions of those. SBA to SBC are the barred spiral galaxies. But wait, there's more. There are the irregular galaxies, IRR, and there are even other classifiers, like the little S in parentheses. That means the spiral arm goes all the way to the center of the galaxy. Or a little R in parentheses means that there's an inner ring present, and I'll show you an example of that. And there's even something called flocculent, which means the spiral arms come in segments. I love the word flocculent. That's just great little word. So it means like the spiral arms break up into little pieces as you go around. And then there's even just a classification of PEEC for peculiar, which just means it's an oddball. And finally, there's lowercase m, which means Magellanic, like the Magellanic Clouds, as in similar to the Magellanic Clouds. By the way, our Milky Way, which I cannot show you an actual photograph of, is classified as this. It's a spiral galaxy, B, capital B for barred, lowercase b, lowercase c, meaning that its degree of winding is somewhere between the B class and the C class in tightness and winding. And so anyway, that's what we think, because obviously we can't take pictures, so we don't know for sure. All right, let's look at some galaxies. This is M87. I showed you a picture of this before as our example of class for the elliptical galaxy. It is an E0-1, meaning it's not perfectly circular. It's a little bit of elliptical in shape. It's a bigger picture here, so you can see those other two spiral galaxies that are hanging out down there. They are behind it and further away. Now, one of the cool things about M87 is in its core, this is a zoom up from the Hubble Space Telescope, it has a central jet, which is the emission from a supermassive black hole around an accretion disk at its core. So this bright thing here is actually the accretion disk at the core of M87 shooting this jet of relativistic electrons in this direction, which then cause the material to glow along its path. So that is one of the reasons why M87 is an object of intense study by astronomers, because of this supermassive black hole at its core. All right, here is a not particularly interesting, it looks like a sun. It's just overexposed in the center because the brightness falls off so much. This is M60, which is an E2 galaxy, meaning it's a little bit more elliptical than M87. Notice, by the way, over here is a part of a very pretty spiral galaxy off, going off stage there. M59, these are all Messier objects. The M stands for Messier. And there was a talk a couple of weeks ago about Charles Messier and his classification of objects in the sky. This is an E5, so it's getting even more elliptical in size. And here is NGC, New General Catalog, entry number 5866, also known as the Spindle Galaxy. Now things are starting to look interesting. You can see this dust lane here. Now, we never know exactly what we're looking at when in astronomy, because projection effects are a big deal. This could be a spiral galaxy edge on, like the kind of like our view of the Milky Way, except we're embedded within it. But we don't know that for sure. And so for classification purposes, this is known as an S0 galaxy for lenticular galaxy. It looks like a lens. It's gone beyond being an ellipse, so you can't classify it as an elliptical galaxy because it's so elongated. It looks more like a lens you might have in a telescope, for example. So anyway, so that's the Spindle Galaxy.
Dan, I have a request that has come in. We have a request for you to please define a black hole, because you talked about black holes recently in one of the last pictures that you had.
I did, yes, that's true. Well, I apologize. I should have defined any term that I use. This isn't a talk about black holes, so I kind of glossed over it. But yes, black holes are the remnants of a massive star that has exploded and created a supernova, which is not a nova, but a supernova. The supernova pretty much blows the star to pieces, but leaves behind a core. And if that core is large enough, it can collapse in on itself. And it's so massive that even the gravity can't stop it from collapsing. And it falls in on itself, and light can't escape from it because of this strong gravity that it has. And since light can't escape from it, it's called a black hole. It turns out that many galaxies, including our own, have black holes in their centers. In fact, these aren't just ordinary black holes. These are called supermassive black holes because many stars fell into these black holes, leaving behind, and basically the black hole keeps growing and growing and growing. So for example, the black hole in the center of the Milky Way galaxy has a mass of 4 million suns. So basically something like 4 million suns fell into this to create this supermassive black hole at the center of our galaxy. The black hole in the center of M87 is something like 10 times that size, so something more like 40 million suns. I don't remember the exact number, but I remember it was something like 10 times larger. So that's, so a single black hole, a regular black hole, is due to just a single star collapsing in on itself at the end of its life. A supermassive black hole is due to many such stars falling into a smaller black hole as it just grows and grows over time. Okay, here we have another galaxy. This is, notice it has these interesting rings of dust around it. Not quite, can't quite tell whether or not it's a spiral galaxy or not. So this is actually a barred lenticular galaxy. I don't know why. The B stands for bar. The S in 0 mean it's lenticular, and the R in parentheses means that there are rings. And you certainly can see the rings. I'm not quite sure why I can't really see a bar here. But I'm sure somebody peered at this more carefully with different exposures and were able to sense some sort of bar-like structure at the center. Right. Here's another curious galaxy. This has its own name, Centaurus A, because it's a very strong X-ray source in the sky. So X-ray telescopes that orbit the Earth, when looking at Centaurus A, this is giving off intense amounts of X-rays. Those X-rays, by the way, are probably due to the supermassive black hole at the center of this galaxy, which has an accretion disk around it. And as material falls into the galaxy, into the supermassive black hole, that accretion disk gets really, really hot and gives off X-rays, which can be observed. Anyway, Centaurus A is also categorized as a lenticular galaxy, but it's peculiar. And yeah, you can see it's peculiar. It has this really, this isn't just a regular old dust lane. This is just some really funky dust structure that's sort of obscuring the center of the galaxy. And it's not clearly classifiable, so it gets the PEEC designation. That was a great question, by the way, about the black holes. And if anybody else has any questions on that or anything else, please.
I do have a question, actually, Dan. I have a question from Aurora, age 8, and she is wondering what is in the Milky Way. And I guess you can also talk to what is in these other galaxies as well.
Let's see. Let me see if I can and think of what she might mean by in. So the Milky Way, and in fact, what you're seeing here in this picture, as well as many pictures, what it looks like, it's like a single object that is glowing, but really what you're seeing are the light from billions and billions of individual stars, which are the stars appear so close to each other from our distance that the light from each of them blends together to give this kind of continuous glow like image. And so that, for example, the Milky Way, the milk of the Milky Way is really just the light from all of these stars that have their light is just kind of overlapping with one another so that you can't see individual stars, you just see the general glow. By the way, I should say the stars that you see in this image are stars within our own galaxy that are very close to each other compared to this object that we're looking at. So these are all the stars, like this here and this here. These are what we call foreground objects that are, you know, only a few hundred light years away from us, whereas Centaurus A is many millions of light years away from us. But all this glow here is from individual stars and with all their starlight merging together. It's too far away to make out individual stars, but you just see the general starlight. The Milky Way is the same. It's made up of lots of stars that are too far away from us to see the individual light. The dust that you see here, or the dust that you see in the Milky Way, this black stuff, is just non-glowing dust that is left over from the formation of the galaxy. I hope that answers at least somewhat your question, Aurora.
Aurora says, so cool.
I agree totally, yeah. All right, here's another beauty. This also is special enough that it has its own name. It's the Sombrero Galaxy. You can figure out maybe why. Also one of the Messier objects, M104. This is designated as an SA. So that means S all by itself means that it's with no zero or anything, means it's a spiral galaxy. A means that it's a very tightly wound spiral. And you might be able to make out that there are kind of spiral bands in here and everything's nice and tight. Now it's so edge on that it's not as easy to see whether the spiral arms quite so clearly. But people have stared at this long enough that they're pretty convinced. Again, all this glow you see here is not just like because it's bright and oversaturated. All the glow is actually from individual stars that are above and below the disk of this galaxy. Here's another Messier object, M51, also known as the Whirlpool Galaxy. And you might, doesn't take much imagination to figure out why it's called the Whirlpool Galaxy. It's designated as an SAB, parentheses, little s. So S means it's spiral, AB means the winding is between the tight winding of an A and the looser winding of a B galaxy. So this is semi-tightly wound, I guess. The little s means that the spiral arms can be traced all the way to the center. So you can see that the spiral arm, you can pretty much follow them all the way into the middle. So some spiral galaxies, that's not possible, like ours, for example. We think they can. Anyway, this is a good point to talk about spiral arms for a moment, because spiral arms are not what you may think they are. For example, the individual stars in this galaxy, or the Milky Way, are all going around the center. They're all rotating around the center. But they're actually rotating around the center much more quickly than the arm structures rotate. Stars will enter and leave spiral arms and go on along their way. The arms themselves are regions of, as you can see in this picture, where the gas density and dust density has gone up a lot. And because of that, there's lots and lots of star formation going on in spiral arms, because when you get a lot of gas together in space, they like to make stars. In fact, the red you see in here are all star factories. And the red is the glow from the newborn stars illuminating the clouds around them. So the actual density of stars in a spiral galaxy is pretty uniform around the whole thing. It's just that when the stars go through the arm structures, they slow down for a while and linger. They create density enhancements of dust. New stars form. Those new stars are also going to move around and rotate around. But the very brightest of those are burn so quickly that they die before they leave the spiral arm. So you get an enhancement of brightness from the biggest, most massive stars within the spiral arms, because by the time they leave, they die. So I have a little simulation here to show that feature. So here we have a simulation of a spiral galaxy. I understand this may look a little choppy on your screens because of the fact that this is over the internet. I apologize for that. We tried to speed this up as much as we could. But anyway, you can see here that the spiral arms are color-coded in blue. The stars between the spiral arms are color-coded in gray. And the stars are moving around, and when they enter the spiral arms, they sort of bunch up for a while, but then they keep on going and they leave. So we have a name for these. We call these density waves in physics. These structures of enhanced density of stars, and so we really still don't have an excellent theory for the formation of spiral arms. There are computer simulations that can cause them to come into formation, but it's still an area of active study. All right, I'm going to continue on. Thank you. All right, more spiral galaxies. This is NGC 4622. And if you think you can see a ring in here, you're right. In fact, that's part of the designation. This is an SAB, parentheses R for ring, because there's what appears to be a clear ring around this middle of it. There's no S here because the spiral, the little S in parentheses, because you can't trace the spiral arms all the way into the center. So there's no special little S here. But the capital S means spiral, AB tells you the degree of winding, and the R tells you that there's a ring. Now here is an SABS. Here, one can trace the spiral arms all the way in. Oops, I didn't go on quite so far. And in this picture, you can't tell that the spiral arms go all the way in. But when we look at this in ultraviolet light, because we have telescopes in space that can see in the ultraviolet, we can trace those spiral arms all the way into the center. So sometimes the information that we get for the designation of a galaxy comes not from just one picture or even one wavelength, but from taking images at different wavelengths. In this case, an ultraviolet image of this galaxy. All right, you've seen this before. I would ask you if this was live, what galaxy is this? And you would say, Andromeda, that's right. Also known as M31, Messier 31. It is designated as an SB little s. So it's not quite as tightly wound as the last one we saw, just a B, not an AB. And little s means, within the parentheses, means that you can trace spiral arms all the way to the center. Again, you may not be able to see it in this picture, but some smart astronomer figured that out. Okay. Now, again, I would ask you, do you think this is an SA, an SB, or something else? And you would probably say, well, Dan, it looks like those spiral arms aren't as tightly wound. I'm going to go with SC. And let's see if you were right or not. Well, first of all, this is the Pinwheel Galaxy. And it is an SC. Yes, you are right. Again, you can see the spiral arms all the way into the center. By the way, this happens to be the very galaxy that Shapley was quoting the results of that astronomer von Manen, who said that he claimed that he could see the pinwheel rotate over the course of a couple of years by a small amount. And that's the observation that Curtis said, I don't believe it. And so this is the smoking gun that was shooting blanks for Shapley's argument. So anyway, but it is a beautiful galaxy in its own right. NGC 2841 is an SB galaxy, but it's also a flocculent. I wanted to give you an example of what flocculent spiral arms look like. And so if you look here carefully, you can see that the spiral arms don't appear to be nice and smooth. They kind of come in little chunks, and hence the term flocculent being applied to it. NGC 1300 has a big bar across it. So it's an SB, capital B galaxy. And lowercase b and c to determine the amount of winding. And S because you can trace spiral arms all the way into the center. And if you look really carefully, you can see little spiral arms way down there in the middle. How about that? We're near the end of the Menagerie tour. This is the Large Magellanic Cloud. This is one of the, if you've ever been to the southern hemisphere of the Earth and you look in the night sky, you can see these two clouds, the large and small Magellanic clouds, and this is the Large Magellanic Cloud. You can see this with your eye. This is not, I mean, this is exposed more because it's a photograph, but this is about what it looks like to the naked eye, just a little bit brighter. This is classified as an irregular galaxy by some, and by some they actually call it a spiral barred Magellanic type galaxy. Funny, that's, I think it's hilarious that they put an M on the Magellanic Cloud itself. That's kind of like, anyway. But they claim that this is a bar here, and some think that there are actual spiral arms, but not very clear, obviously. And here's the small Magellanic Cloud. Again, this is over, or a much deeper exposure than your eye would see, but it's about the size. You would see something kind of like this in the sky. It's also designated as an irregular, or, and I love this, irregular Magellanic. Well, how could it be irregular Magellanic if it's a Magellanic Cloud? I ask you. I think it should just be M, but don't make these decisions. All right, so there's all this amazing structure out here. Did it just happen to form that way, or all these different galaxies, or what caused the galaxies to have the structures they have? Well, it turns out, and this is actually fairly recent astronomy, I would say within the last 30 years, people figured this stuff out. That a lot of the structure that you see are due to galaxy collisions and mergers. That is, galaxies literally crashing into each other. So for our first example of that, let's go back to the Whirlpool Galaxy. As you see here, this actually is two galaxies. You can see the main part of the Whirlpool Galaxy here, but look at over here. What the heck is that? Well, that's another galaxy that happened to lose its way and fall in to the Whirlpool Galaxy and then went back out of it again. And we actually have a simulation to kind of show how that happens. So here is the little galaxy coming in, and it distorts and it actually causes the spiral arms of this galaxy to form. And here is that visiting galaxy that kind of got ripped apart in the process. Very cool, fun simulation. Lots of computer CPU time. And there you go. And then they speed it on. And then finally, that thing gets completely disrupted and absorbed and cannibalized into the main galaxy. And then you get a beautiful symmetric spiral galaxy as a result.
Dan, we had a question about how far apart those two galaxies are, the Whirlpool and its companion.
Well, in the actual photograph here, I'm going to guess that the Whirlpool Galaxy is about the size of the Milky Way galaxy. So that would put this other galaxy at about 100,000 light years away. So it's quite well connected to the Milky Way here. I'm sorry, to the Whirlpool Galaxy. And I want to point out, in this original simulation, there were no spiral arms. The spiral arms actually formed as part of the collision. And in fact, a lot of people think that spiral arms need a collision to get them to come into existence.
I also want to point out, that, Dan, that it is about 8 o'clock right now. So just keep that in mind.
Yes, so we are very close to the end. I just wanted to show you some of these images, these cool images of the simulations of how all this structure could come into existence. So here is another simulation of a flat galaxy and a kind of a incoming galaxy. similar to this, which is the Cartwheel Galaxy. So let's go back to the simulation and let it run. And so this other galaxy, kind of the small galaxy, went through the middle of the Cartwheel Galaxy and created these rings and spokes that are then seen in the actual Cartwheel Galaxy. Here, you can see the ring and the spokes. So, all right. I have one more simulation that I'll do. These are, imagine two disk galaxies coming along, maybe spiral galaxies, and they interact. And crazy things happen. Look at that. And the guy who made the simulation got a little excited here, spinning it around and showing it from different views. The reason he's doing this is because if we look at some actual structures in the sky, we see things like this. This is NGC 5426, 5427. They're in the midst of kind of the early parts of that simulation. And I have to warn you that this is what's going to happen to the Milky Way and Andromeda in about 4 billion years. We are on a collision course with Andromeda. And you had to wait a long time. I wouldn't worry too much. But this is that simulation you just saw is a prediction of what will happen. By the way, we do see other colliding galaxies that look like this, that simulation just showed, like this, and like this. And I think with that we'll leave it. So basically the bottom line is that as galaxies collide, they create a lot of the beautiful structures that we see. And elliptical galaxies are the result of many, many collisions over time, multiple galaxies chomping on each other. And eventually you lose all that structure and you're left with, in fact, in this image here, you can see an elliptical galaxy up there. This kind of bright, large, undifferentiated ball of stars from multiple collisions over time. And that's why elliptical galaxies can become so large, like 1,000 times the size of the Milky Way, because they've eaten up all these other galaxies over time. Now, the individual stars, I have to make this point very clear, don't necessarily get destroyed in these collisions. The distance between the stars are still vast. This is all kind of like long distance action, but the structure that the stars have gets very disturbed by these collisions. All right, and with that, I thank you for your attention, and I hope you have a good evening. And I'm happy to hang out for a little bit longer for some questions if there are others. But otherwise, I appreciate your time.
Hey, awesome. Thank you so much, Dan. That was cool. And I think, let's see, we do have a couple other questions. And one of them, I think you just answered. Marcy asked why there were different shapes of galaxies. And I think you just got into that at the end with all the collisions and weird stuff that happens when these two things collide. And then she also wants to know, how old is the oldest galaxy?
Well, that's a very good question. Well, I actually have, as in backup here, if you an image, let's see, of this is a picture of nothing but galaxies. This is the Hubble Extreme Deep Field Survey, and taken by the Hubble Space Telescope. And the oldest galaxies in this image are 13.2 billion years old. Now, the universe is 13.7 billion years old. So the oldest galaxies in this image are only 450 million years since the Big Bang. That's basically, we think galaxies started forming about 200 million years after the Big Bang. And these are the earliest galaxies. Every single thing in this picture is a galaxy except for three. There are 3 stars in this image. Otherwise, everything else is a galaxy. When you look far enough, deep enough, long exposures that the Hubble Space Telescope can provide.
Okay, awesome. So we see galaxies that are over 13 billion years old. So almost the same as long ago as the Big Bang. We've had
just
galaxies.
Yeah, 13.2 versus 13.7 billion years.
Okay, half a billion
very,
years.
very old. Yeah.
Okay, great.
Our Milky Way is maybe about 12 billion years old, by the way. So
very old in our time scale. A galaxy is an old thing. Let's see. Okay. Another question about our solar system. Is our solar system inside or outside a spiral arm of the Milky Way? And how would it look different if it were in the other thing?
So if we go back to that picture of the whole Milky Way here. So the sun is right down here, and it's in a spiral arm called the Orion Spur. And the entire solar system would be a pixel on this image. Just, it would not even be a dot at this scale, to be clear. It's a really good question, though, about what it would look like if we were not in a spiral arm. If we were not in a spiral arm, there wouldn't be as many close by stars in the sky. We would still see the Milky Way just fine, but the general star field that we would see would be less dense than it is where we are. The local stars, there wouldn't be as many of. But the long range horizon, the distant Milky Way would look pretty much the same. In fact, it might even be brighter because there wouldn't be local gas obscuring our view of the center of the galaxy as much.
Cool. Okay, so that is kind of a fun thing to think about. Like, what would it look like if we looked at a different part of the Milky Way? So another question, from what we can see from Earth, does it seem like there are types of galaxy structures that are the most common? They're common types, uncommon type?
Well, the spiral galaxies are more common than the elliptical. Within the spirals, it's interesting. We're kind of in an upper class galaxy. I mean, this is called a grand spiral galaxy, and it's one of the larger spiral galaxies. There are many more smaller spiral galaxies than ours, than the size that we are. So in fact, it goes down to this distribution called dwarf spirals. And the dwarf spiral is the most common class of spiral galaxy. Those are the ones that have only, 1 billion stars in it, not 100 billion stars. So we're kind of special in that way.
Okay, cool. And now someone is wondering how long a galaxy collision or merger would last.
That's an excellent question. Yes. Well, it kind of depends. The time scale for those simulations that you saw just a minute ago, every step that you saw was about 1 million years. Like every frame of the movie advanced time about 1 million years. So a typical collision will last for something like 500 million years. So like 500 million years. So these happen very slowly. It's collision in slow motion. So we would have plenty of time to duck. So to put it in perspective.
Okay, so then Galen is wondering if galaxy collisions produce elliptical galaxies, should there be fewer ellipticals the further back we look into the universe?
Yes, and there are. But there are more just like there are lots of small spiral galaxies, there are also lots of small elliptical galaxies. And so when you look back in time by looking into the deeper field, you just see lots of small elliptical galaxies. It only takes, if conditions are right, it only takes one collision between two spiral-ish galaxies to create an elliptical. It depends on how much net angular momentum they carry after the collision. So like if you have one spiral galaxy spinning one way and another spiral spinning in the opposite way and they collide, at the end, they'll have no spin left. And that's kind of when you get an elliptical galaxy. So you can have small elliptical galaxies as well. And if you looked in that Hubble Deep Field image, you could see that there were elliptical galaxies as well.
Okay, great. So then I have one last question. And Gary is wondering if you believe that there is life in outer space.
Well, I guess the short answer is, and this is belief because we don't have any evidence, the short answer is yes, I do. There are so many, there's 100 billion stars in our galaxy. There are hundreds of billions of galaxies. So the chances that we are the only star that had a solar system, and we also know now that pretty much every star has a solar system because we can see planets around, individual planets now around other stars. And so just, you know, going with the odds, the chances of life being elsewhere in the universe is extremely high, I think.
Okay, cool. Well, Dan, thank you so much for your talk tonight. I found that was really fascinating, and just the pictures are beautiful. It's so amazing, the variety of galaxies that are out there.
Yeah, I know. It's really fun to look at them and actually start to think about the structures and such. So yeah, well, thank you, and thank you for all those great questions too. That was really appreciated.
Thank you, everyone, for tuning in and for asking your questions. Those were fun questions, and I appreciate that too. And I want to thank you all for tuning in. Have a good night and a great weekend.